After studying this module, you shall be able to know about ion exchange resins, learn about Donnan equilibrium and Donnan potential, differentiate between cation exchange resins and anion exchange resins, calculate the stability constant on the basis of ion exchange chromatography. Ion exchange chromatography. In the ion exchange chromatographic method, the retention of a solute on the resin is based on the attraction between solute ions and the charged sites bound to the stationary phase on the resin. What are ion exchange resins? The ion exchange resins are composed of amorphous organic materials. One common ion exchange resin is made by the copolymerization of styrene and divinyl benzene to yield polystyrene, as shown in the figure. The extent of cross-linking of the insoluble polymer is varied by varying the divinyl benzene content in the polymer. Modifications of the benzene rings result in the formation of a cation exchange resin containing sulfonate groups or an anion exchange resin containing ammonium groups, as shown in the figure. If methyl acrylic acid is used in place of styrene, a polymer with carboxylic groups results. The sulfonate groups containing resins result in strongly acidic resins, where the sulfonate groups remain ionized even in strongly acidic solutions. Carboxylic group containing resins are weakly acidic resins, which function below a pH of 4. Quaternary ammonium groups remain cationic at all values of pH and are strongly basic. Weakly basic tertiary ammonium anion exchangers are deprotonated even in moderately basic solutions and lose their ability to bind to anions. If the immobilized surface was coated with immobilized anions, then the chromatography would be termed cation exchange chromatography, and the cations would selectively bind and be removed from the solution flowing through. If the immobilized surface of the resin was coated with immobilized cations, then the chromatography is termed as anion exchange chromatography. The immobilized cations will have electrostatic attraction for the anions. The ionic species bound to the column can then be removed, that is eluted and collected by changing the pH of the solution. Let us now discuss the properties of the resin. The extent of cross-linking determines the rigidity and porosity of the resin. The resin becomes more rigid and less porous as the cross-linking increases. Lightly cross-linking resins permit rapid equilibration of the solute between the inside and the outside of the resin particles. However, resins with little cross-linking swell in water. Hydration decreases both the density of the ion exchange sites as well as the selectivity of the resin for different ions. More heavily cross-linked resins exhibit less swelling and higher exchange capacity and selectivity, but they have a longer equilibration time. Let us now talk about the Donnan equilibrium. When an ion exchange resin is placed in an electrolyte solution, the equilibrium established between the ions in the solution and the ions inside the resin is called the Donnan equilibrium. When an ion exchange resin is placed in contact with the solution, then there is a natural tendency of the mobile species to reach equilibrium. When the hydrogen form of the resin is placed in a solution of hydrochloric acid, diffusion forces will try to level the difference in the concentration of the hydronium ions. The mobility of the hydronium ions is prevented due to the immobile ionic sulfonate groups of the resin. If even a minute amount of hydronium ions leave the resin, electroneutrality is disturbed. This prevents the hydronium ions from leaving the resin, and an equilibrium is established even when non-measurable small amounts of hydronium ions leave the resin. The concentrations of the hydronium ions and the chloride ions are almost the same as they were before the two phases came in contact, but a large potential difference now exists between the phases. This potential difference is called the Donnan potential. Let us discuss how the ion exchange resins can be used to determine the stability constants. Let us discuss the principle of the method. The metal ion distributes itself between the ion exchanger and the solution phase. Studying the distribution equilibrium helps us draw conclusions about the degree of complex formation of a metal ion with a ligand in the solution. The stability constants and the overall stability constant can then be evaluated. Cation exchange resin, an ion exchange resin or a liquid ion exchanger can be used to carry out these experiments. The ion exchanger used in the experiments should be a strong cation or a strong anion exchanger. If a liquid ion exchanger is used instead of an ion exchange resin, the pH should be kept constant throughout the series of the experiment. Let us discuss about the cation exchange resins. For studying the metal ions of the small size, a medium cross-linked cation exchanger is suitable. The metal ion concentration used for the experiment should be low. For each experiment, the same counter ion in the same concentration should be used. The counter ion is non-complexing, but determines the position of the ion exchange equilibrium. When the ligand is a multivalent large anion, larger in size as compared to the metal ion, the complex formed between the metal ion and the ligand will be strong. Only the free metal ion, that is the aqua complex, binds to the resin then. Consider the equilibrium that is established by the metal ions between the cation exchange resin and the aqueous solution in the absence of a ligand, that is, in the absence of a complexing agent. If the univalent sodium ions on the cation exchange resin are exchanged with a multivalent cation, the following equilibrium is established. The metal ions displace the sodium ions from the resin. So, the Mz plus metal ions are replacing Z sodium ions from the resin as shown in this equation. The equilibrium constant is given by the value of K as shown in the equation. Here, the concentration of the metal ions and the sodium ions in the ion exchange resin is given in round brackets and the concentration of the metal ions and the sodium ions in the solution is given in square brackets. The distribution coefficient of the metal M between the resin and the solution dm can be then expressed as the concentration of the free metal ions in the resin over the concentration of the metal ions in the solution as shown in the equation. If the concentration of the metal ions is much smaller than the concentration of the sodium ions, then sodium ions are considered constant and the value of dm depends on the concentration of the sodium ions in solution. Now, consider the equilibrium that is established by the metal ions between the cation exchange resin and the aqueous solution in the presence of the ligand, that is, in the presence of the complexing agent. In the presence of multivalent complexing agent ligand L, the distribution coefficient is given by dm, which is equal to the concentration of the metal in the resin as represented in the round brackets divided by the total concentration of the metal. The total concentration of the metal will be equal to the free metal ion concentration plus the metal complexed with the ligand L forming a 1:1 complex, the metal forming a 1:2 complex with the ligand, and so on as depicted in the equation. Assuming that the concentration of the sodium ions in the solution is the same in the presence and in the absence of the ligand, that is, in the presence and in the absence of the complexing agent, and dividing equation 3 by equation 4, the fraction is obtained. This fraction is labeled as Am. By measuring the distribution coefficients of the metal ion in question in the absence and in the presence of the complexing agent in solution of the same ionic strength, we can determine the value of Am L at different ligand concentrations. Rearranging the above equation, we get this equation. On plotting the left side of equation 6 against the free ligand concentration, we obtain the value of beta as the extrapolated intercept of the linear part of the curve. Rearranging the equation, we get AML minus 1 divided by L minus beta 1 divided by the free ligand concentration. After determining the beta 1, a plot of the left side of the equation 7 against the free ligand concentration gives us the beta 2 value as the intercept of the curve. All beta values can thus be determined in this manner. The graphical representation is commonly called a Schubert's plot. If the metal ion is in an oxidation state much greater than the negative charge on the ligand, then positively charged complexes are also formed. These positively charged complexes may be adsorbed by the cation exchanger. This also has to be factored in while calculating the stability constants. Let us see how an anion exchange resin can be used to determine the stability constants. For studying anions of small size like the halide ions, the cyanide ions, a medium sized cross-linked anion exchanger is necessary. When the ligands are smaller in size, the negatively charged complexes formed between the metal ion and the ligand can be absorbed by the resin. That is, the negatively charged complex can replace the anions in the anion exchange resin, assuming that the ligand has a univalent charge like chloride ion, cyanide ion with one negative charge, and among all the species formed with the metal ion, only the mononuclear complex with charge P are bound to the ligand. The following equilibrium is then established for the ion exchange reaction, in which P ligand ions bind to the resin and displace the ligands, anionic ligands already bound to the resin. Here P is the negative charge on the complex and is given by N minus Z, where N is the number of ligands bound to the metal ion and Z is the charge of the metal ion. The equilibrium constant for this reaction is then given by Kx as depicted in this equation. If the amount of the metal ion is very small as compared to the capacity of the resin, then the concentration of MLN is much smaller than the concentration of the ligand, and the ionic strength is a constant. Kx then may be considered independent of the concentrations. Multiplying both the numerator and the denominator by Cm, we get the value of Kx as shown in the equation. The MLN concentration, that is the concentration of the metal ligand complex in the resin, divided by the total concentration of the metal ion, is the distribution coefficient of the metal. The reciprocal value of the mole fraction of the complex species is given by the total concentration of the metal ion divided by the concentration of the metal ligand complex in the solution. The mole fraction is then represented by phi. Rearranging the equations, we can find out the value of dm as depicted in this equation. If Kx and L are constant, the distribution coefficient dm is a function of the ligand concentration and the mole fraction of the complex species bound to the resin. Taking the logarithm and differentiating the equation with respect to log L, we get equation 13. The term d log dm divided by d log L refers to the average charge number. The average charge number is related to the ligand number by this particular equation as depicted in equation 14. It is represented by P bar. The log D versus log L curve has a maxima as shown in figure and a part of a negative slope if a negatively charged complex species is formed. At the maxima, the slope is 0 and the value of P bar is 0. The uncharged species predominates. For a univalent ligand, the ligand number is equal to the oxidation state of the metal. Let us now discuss the limitations and precautions one needs to take while determining the stability constants of a complex by using the ion exchange method. For calculating the stability constants of complexes with low stability, experiments should be performed at high ligand concentrations. Perchlorate ions are generally used to maintain the ionic strength of the medium, as they are poor complexing agents. In solutions with low ligand concentrations, the perchlorate ions can be strongly bound by the resin. Above a certain ligand concentration, that is the free ligand concentration L, or L cannot be considered a constant and the equation needs modification. To determine the distribution coefficients, it is advisable to use the static batch method. In this technique, the ion exchange resin and the solution are mixed in a batch vessel. The exchange is allowed to come to equilibrium and then the resin is filtered off from the solution. The extent to which the ions are exchanged on the resin depends on the selectivity coefficient of the resin. The time required to attain the equilibrium is determined by the rate of diffusion, and the two phases should be stirred for an approximate length of time, that is several hours, so that they reach equilibrium. The concentration of the distributed component can then be determined spectrophotometrically. Let us discuss the summary. In the ion exchange chromatographic method, the retention of a solute on the resin is based on the attraction between the solute ions and the charged sites bound to the stationary phase on the resin. If the immobile surface of the resin has immobilized anions, then the chromatography will be termed as cation exchange chromatography. If the immobilized surface is coated with immobilized cations, then the ion exchange chromatography is termed as anion exchange chromatography. The immobilized cations will have electrostatic attraction for the anions. A cation exchange technique for measuring the stability constant has been developed by Schubert. This technique requires that the complexes formed have a 0 or a net negative charge. If a system consisting of a metal cation, the chelating agent and a cation exchange resin, then the amount of cation absorbed by a definite amount of the resin is proportional to the concentration of free cations over a wide range of concentrations. The distribution coefficient of the metal is determined in the absence as well as in the presence of the chelating agent in solutions of matching ionic strength. The stability constant can then be determined from the equations discussed. Fornes has developed a method of treating data from ion exchange experiments which permits the calculation of successive formation constants, including those of cationic species.